satisfied. One, there needs to be no overtopping. Okay, and then a dam should be saved against overtopping during occurrence of the worst flood. So this is why we provide spillway. So no overtopping, because if overtopping occurs, there will be erosion. Yeah, and then erosion, eventually you will not have a dam. And B, an adequate freeboard should be provided so that dam is not overtopped due to the wave action. Again, we said there is the free the free is called free what freeboard, is it freeboard? The height the freeboard height should at least be 1.5 times the height of the wave. You remember that, to avoid overtopping during wave. Then C, a suitable allowance in the height of the dam should be made to account for settlement. Of course, we are dealing with the soil, and there will be settlement, of course, ipso facto. So we said at least 1% of the height, if the height is above 30 meters, so 1% of 30 is in the range of, I think, quick calculation, 1% of 30 300 millimeters if the height is 30. So of course there will be settlement, that's the point, and you need to make adequate provisions for this. Then we need to show seepage. Remember, I already talked about this, how to you need to check that the seepage is not too much. First, seepage, because if the function is to impound water, then if too much seepage occurs, that means you will not be impounding any water. That's the first thing. Number two, if not, the flow can transform to erosion, and then you eventually will not have a dam. As well, phreatic line or seepage line should remain within the downstream face of the dam so that no sloughing of the downstream face occurs. Seepage through the body of the dam foundation and abutment should be controlled by adopting suitable measures. We said you always provide some filter. Filter can be made of wood, can be made of steel, can be made of clay. Filter can be made of bituminous mix. Filter can also be made of concrete. You remember all that? Yes. The dam and foundation should be safe against piping failure. If the in situ material is sand, there should be no opportunity for free seepage of water from upstream to the downstream, either through the dam or through a foundation. There should also be no structural failure, of course. The upstream and downstream slope should be safe during and immediately after construction, and even after the construction. The upstream slope should be safe during sudden drawdown condition, yes, and this is a challenge because let me demonstrate here. So if this is your dam, if this is your dam, and then so this is the condition. Then suddenly you draw the water goes down to this level. This is quite dangerous because here there is a balance of poor water pressure here. So once you remove the water here, the balancing action of this water is not there, and then the slope will tend to collapse. That's the issue. So still you need to take care of this condition. So even if there is a drawdown, rapid drawdown, the dam should still be safe either way. Also, the downstream slope should be safe during steady seepage conditions. The foundation shear stresses should be within safe limits. The dam as a whole should be earthquake resistant. Of course, you're lucky that this country experiences minimal earthquakes, but either way, actually we are going to also talk about earthquake because I don't think you're being trained only to practice in this country. You can once you have a degree, you are universal. You are a universal engineer. You can work anywhere. We equip you to be a universal engineer. So we are also going to talk about how to design for earthquakes as well. Whatever you do with that information is up to you, but we make you a suitable universal engineer. You can work anywhere in the world. We are not only training you for Kenya. If you can fit in Kenya is fine, but you should also fit in the rest of the world. Number 4, proper slope protection. The upstream slope should be protected against erosion by the waves, of course. The waves have some energy, a lot of it, so that energy needs to be dissipated conveniently, such that the upslope is not eroded, upstream or upslope if you like. The downstream slope and the crest should be protected against erosion due to rain and wind. The downstream as well should be protected. So you usually there is some riprap. Okay, depending on the type of dam, there's some riprap on the upstream. Riprap to absorb the wave energy and dissipate absorb the energy so that there is no erosion. Now on the downslope or downstream, usually we plant some vegetative cover, of course, and then proper drainage portion of the dam downstream of the impervious core should be properly drained. You need to provide proper drainage as well. The economic section, the dam should have an economic section as far as possible. The materials available near the dam should be used to reduce cost. If for example the length should be the minimal length that can serve is 20 meter, for example. There is no reason why you should have 30-meter dam. So if the cost-effective design is 20, that is what you should provide, because again, all this trouble we go to is to make sure we have an economic design. So do not over design if that is not the case. So we start first and foremost by the Swedish method. This is the a way to estimate the stability. I'm sure you have been introduced to this before. Now, the Swedish circle method is the most common because it's quite simple as well. Please register your attendance on the chat box. The name, number, the name and registration number. The Swedish circle method is the most common, and the method for checking the stability of slope. The method is general and can be used for homogeneous as well as non-homogeneous masses. Stratified deposits for partially or fully submerged conditions or dry conditions. However, the method is necessarily an approximate one because it neglects the effect of forces acting on the side of the vertical strips. Fortunately, the Swedish slip circle method errs on the safe side because the factor of safety obtained by this method is less than that obtained from the more accurate methods. So this method is a little bit conservative, but is simple. So this is why it is preferred. The method therefore can be safely used in practice. In the Swedish slip circle method, the least factor of safety of about 1.3 to 1.5 is usually specified in the stability analysis of earth dams. In conventional Swedish circle method, it is assumed that the reactions ER and EL are equal and opposite. I'm going to show you this in detail, and cancel each other and do not affect the equilibrium. Likewise, it is assumed that the forces due to pore pressure UL and UR are two sides also balance each other and do not affect the equilibrium. So the the point here is that I'm sure you are aware of this. You just draw the slope to scale. Once you draw the slope to scale, then you decide the width, and you consider the equilibrium of each of those slides. I'm sure you know how to do this. The self weight and the component based on the orientation to the original. I mean to the not original orientation to the horizontal, and then you can do your calculation. But I need to explain this. This is your and then you've divided them into several slides like this. Now the issue is in actuality or in reality, there are some forces here that we ignore on the side of these slides, because you can see here we are only talking about the self weight, and then based on this angle we resolve, for example, n, and then these components. So we are only dealing with the more or less vertical forces, but there are some forces here. Actually, I'm drawing my own, but is explained here. These horizontal forces here, you can see ER and EL. So we see that they are equal and opposite, but in actuality they are not. Again, there could be pore water. All right. So we assume those, and they say they are equal and opposite. But because this method is simple and gives us conservative values, which are more or less leads to safe design, so it's still acceptable. So this is the point. So I think you have been introduced to this in fourth year. So after you divide, the idea here is the slope, you somehow have to determine the center of rotation, or the center of the slip circle. Once you determine the center, you draw the slope to scale, everything to scale basically. Then you decide the length, or the width of each slide, and you find the area, because now this would be kind of a regular shape, would be like a trapezium whose area you can find easily. Based on the area, you assume a unit weight in the direction perpendicular to your eyes, so that means the area would be the volume basically. And then you resolve, because the weight, the self weight, will have a normal component in this direction and a shear component, and then you sum all of them together. And then you can see that this the slope, you can see the excuse me, the factor of safety is about the summation of driving forces against the resisting forces. Now, I need you to see, I need you to, okay, let me, maybe it wouldn't be very clear here. So just to show you the so the I believe some of that, the way that the anyway the just a minute, please excuse me 1 minute. Okay, you know that the factor of safety is the sum of resisting forces over the sum of driving forces. Now the resisting forces have some things to do with the shear strength. You remember we said shear strength is C plus sigma tan phi. So anything related to the shear strength is resisting the movement. Now the self weight, you can see the self weight is trying to pull this slope downwards. Now the shear strength is acting along the slip circle in the opposite direction. So those are the resisting forces. The driving forces are associated with the self weight of the slip slope. So that's, once you understand this, then you sum up the driving forces and the resisting forces, and then you can actually get the self weight, I mean the factor of safety against sliding, this downslope sliding. Thus there are four forces which are normally considered: the weight, this is the shear. I don't know, I think maybe they are shown here or in the next slide. Yeah, they are shown in this you can see R there, U, yeah, they are shown in the notations are shown in this figure 2.10. So the considered W, for which has nothing to do with the weight. C is the shear related to the shear strength. R is the reaction, is related to sigma. We said R is the perpendicular force, so to speak. You can see there R, and UB is the pore water, related to the pore water pressure. If you don't have it, the things are much simpler. Even if you have it, still it doesn't matter. It can be dealt with. So the force UB due to pore water pressure is 0 if the soil is dry. So things are simpler, and the number of forces in that case reduces to only 3, which you can easily solve. And this method is preferred because it's simple. Though conservative, it leads to safe design, so you don't need to bother with a lot of issues. So for manual work, this method is the way to go. But sometimes, or these days, we use a lot of computers to solve most of these problems. So you don't need to worry so much with the manual. Of course, as an engineer, you need to be aware of, or you need to know the basis upon which these softwares solve these issues. So 2.10 shows a portion of the slip surface for slice. Let us resolve into normal n and the tangential t. As the normal of a circle passes through the center, the direction of n first marked in the normal direction, perpendicular is drawn from the tip. The vector w normal to determine n t and t. Thus, so this is just to show you how to resolve the components. I think you're in fifth year. This is beyond. This is much too simple for this level. You should know how to resolve. I think should be very simple. If the angle is here, there's no way where you can see this is that's a sine or a yeah, cos. If this is the angle, uh, if this is the angle, then this is w cos theta. I mean, it's too simple to, and this is uh, sine theta. I'll leave that for you. That one should have been done in physics in first year, and where the normal components are calculated considering the submerged unit weight, or WS, or gamma sub of the soil, and the tangential components T are calculated considering the saturated unit weight. So the factor of safety of slope is determined from. So if you're talking about total stress parameters, then you ignore the pore water. If there's pore water, you need to consider, because pore water has to be subtracted. So then the factor of safety is so the summation of, you can see here we are subtracting the pore water, so tan phi or tan theta, not theta. Please don't confuse the two. Phi is the a soil parameter, and theta is the orientation. So please don't confuse those two things. Uh, so you know the shear strength. The shear strength of the soil is C plus sigma tan phi. So the phi, this is the phi we are talking about. Now theta is the orientation, theta is this. This has a slope somewhere, so this is the theta. That's the theta. So that's what. So don't confuse that to those two things. So tan phi plus the summation. We're talking about the summation because you have several slips, so you need to consider those slips in each individually, and the weight is the area times the unit weight. The submerged unit weight you'll be told times the area of those individuals. Theta is the angle. I've already defined that, and then the pore water if it's there. This secant, that's a trigonometric quantity. Then plus the cohesive part times the secant, and then this. So these are the resisting forces. You can see they are all related to the shear strength parameters. All right, and then divided by the component of self weight. So if the soil is dry, that means this part is not there. The equation simplifies to 2.6. So there is a procedure here for the detailed procedure of how to solve this part. The procedure for the determination of the factor of safety of tile slip cycle. Also, sorry. Also, you need to be aware that okay, we have made it here very simple to enhance the understanding, while in fact it's in reality it's quite a little bit more tedious than what is presented, because you have to try several slip circles and you take the one with the least factor of safety. So once you have been given the geometry, it's not very easy to determine the center, the actual center of the slip circle. All we know is failure will tend to go to happen in a slip circle manner, but it's not clear. It's not immediately very clear where. So you have to try several slip circles, get the factors of safety, and then choose the one with the least, because that is the critical slip circle. That is in the ideal situation. Now for examination purposes, you'll be given the slip circle, an assumed slip circle, and your job will only be to get the factor of safety. While in reality, as an engineer, you have to be aware that the factor of safety, I mean the critical circle, it's your job to determine the critical circle. For those just joining, please record your attendance, write your name and your registration number on the chat box. Yeah, so you have to be aware that you need to try several circles and find the one with the least factor of safety. That would be the critical circle, so to speak. So take a tile slip surface and divide the wedge above the slip surface into 8 and 15 sides. Now this is a suggestion. You can do your own due diligence. You can change. They don't have to be 8 or 15. The key is the smaller the length, the width of the slide of the slip, the more accurate, but of course the more difficult your job is. Of course, you need to find some critical width. Beyond a critical width, probably further reducing the size will not bring a big difference in the factor of safety. So for example, if the critical width circle is let's say 2 meters, and with 2 meters you get a factor of safety of 1.91, right? And then you reduce maybe to 1.5, then the factor of safety is still 1.905. So you can see by reducing the size, you are not bringing a big difference in the factor of safety. So so this is a judgment call again on you as an engineer. So Now that will leave to you to see, but the idea is the smaller the width of the slip circle, the more accurate is the factor of safety. So that would be up to you. Determine the weight of each slice and its line of action. For convenience, the weight of the slice is generally taken proportional to the middle ordinate of the slice, and its line of action is taken through the middle of the slice. So these are just some pointers. But all is described here already. That if you take this is your slide, of course the weight will be acting exactly at the midpoint. Yeah, that's the assumption in that case. I mean, from geometry that should be true. And then the weight already told you that is the so the assumption here again is assumed that these if they are so small, if these slips are so small, then in fact you can assume that this is a rectangle. So it's just length times width. But if you want to be more accurate, this is a trapezium more or less. So you can use this length plus that length divided by the width. Yeah. So this is just the area of the slice, and I said the area. In fact, to get the weight should be the volume times the unit weight. But we're saying this is the area because we are assuming a unit weight, a unit length in the direction perpendicular to your eye, so perpendicular to the slides. So that means the area is the same as the volume. This is how you can get the weight, the self weight, and the Z is the middle ordinate. So this one is assuming the weight, the area is length times width, but in fact that's a trapezium, which you can add the two sides, get the area, and then multiply and see how much difference that makes. So measure the angle phi, which the normal makes with the vertical. Compute the normal component. So this is the angle I don't know. This is the angle theta. This is the this is the angle theta. Yeah, that's the angle to the normal. Should be clear. Yes. So theta, it's written here that in a funny way, but the point. Measure the angle theta which the normal makes with the vertical and compute the normal. Yeah, and then determine the cohesive force CB as secant theta. Determine the factor of safety for the tile slip. From the equation, we already said summation of this one. Either this, whether there is pour water or not, any of those equations. And then so this is the correct method for your practice as an engineer. So repeat procedure for a number of tile surfaces. The tile surface which gives the minimum factor of safety is the most critical circle. The minimum factor of safety should be greater than the specified value, which is between 1.3 and 1.5. So this is what I expect from you in your in the exercise, in the design exercise. Now you have to, once you obtain the geometry and the placement in the area, you have to try several slip circles, at least more than one. And then you choose the minimum slip circle. Now that is to show that you are gearing up to be a real engineer. Now the to some clarification on this C, there is usually this uh, because students will confuse this many times. So when you do the experiment and you get tau equals c plus sigma tan phi. Now this C is usually, for example, if we were told is 20 kPa. kPa is kilonewton per millimeter per meter squared, for example. Now when you have uh, when you have length here, this is a whole length. So if, unless you are told specifically, then you take that the 20, if for example is 20, is for the whole length. So if you want to get per unit length, you have to determine that the entire length, which of course would be the angle this extend to the center. I don't know how you want us to call it, angle. Let's say, because theta and phi are already taken, okay, let's say theta 1, and the center would be, the length there would be theta 1 over 360 times pi d. That would be the length. So let's say it's L1. So if you want to get per unit length, here would be 20 times divided by L, and this value would be kilonewton per meter squared per meter. All right. So the units would be different. Kilonewton, whatever value it is, would be say 20 divided by L1, but I'm concerned of the units, kilonewton per meter squared per meter, because it's cohesion per unit length. All right. So if you want to deal with the so I'm talking about how to solve this value, how to get this value, C. So this is the unit, the unit. So CB is like, you have to multiply. If you have the unit, I mean the cohesion per unit length, then you multiply by the length that is required, because you'll be having individual slides. So the unit length has to be multiplied. The unit length has to be multiplied by the length, this length of each slide. But of course, the cohesion is per unit length is constant, and the length of each slide, because you have divided it into two equal parts, then that should also be a constant value. That should also be a constant value. So that should be no problem. So I hope that is clear. You don't confuse that when doing your research. And so once you do that, then you're able to solve your problem. Then you are able to solve your problem. So there is an example demonstrated to you there. An earth dam has been made at an angle of 30 to the horizontal. The radius is 40, passing through the toe of the dam and through a 0.8 meter away on the crest from the edge of the earth dam. You can see cohesion here is 15. So that means the cohesion for the entire length, you have to find the cohesion per unit length. Theta is 30. This is phi or theta. I think this is phi. is 30, gamma is 18, the depth of the dam is 20 meter, depth of the earth dam is 20. Check the stability of the upstream by the Swedish circle method. Now this has been made quite simple for you. You need to use the procedure to see whether you can get that value. Now, as a good student, you should, after this class, you should just go and make sure you're able to do that. So this should be fine. Let's see. So this should be fine. Yes, this should be fine. So as a good student, you should go after this class, you make sure that you can find that factor of safety and see all these figures the way they are obtained. Okay, so that's 1.6 greater than 1.5 is safe. Oh, and actually this, I think this is spoon feeding. So this is the scale diagram already shown for you, and this is how the yes, so everything actually has been done for you. However, I want to challenge you. So this is this addition of each slide. Is fine for you, but please, I think the way he has found the area is a little bit too simplistic. So repeat this because these are in fact trapeziums, not rectangles the way he has assumed them. So see how much difference will it will make if you take this as trapeziums, and of course these are more like triangles. The ones at the edge, at the extreme ends, are more like triangles. See, and then that would be more accurate. And even if this is already done, please make sure you can repeat, and at least you understand the nitty-gritty of how to do this and how to sum and add. Yeah, so that's assignment for you. So and then I think we can take a pause there for 5 minutes. We resume at 8:15 unless there's a question. Class rep. So we proceed. There is a approximate method. The issue with these approximate methods, sometimes they are not as accurate. Nonetheless, sometimes you need to obtain some figures to use rapidly. For these reasons, it's important they can give you an idea very fast when you don't have the time to do more rigorous methods. So the stability of upslope and downslope of an earth dam can be checked an approximate method by considering horizontal shear developed at the base of the dam. The method is very approximate and rarely used. In practice, the method can be used for preliminary design. I think I already said that. Uh, yeah, preliminary design when you need the results relatively fast and you don't have the time to do due diligence. I mean, not due diligence per se, but you don't have the time to adopt more rigorous methods. Of course, after you use this approximate method, then of course you have to confirm with a more rigorous method. The method can be used for preliminary design or analysis. Method is explained below for the following cases: overall stability of the dam, stability of downstream slope, stability of upstream slope. Overall stability of the dam. The overall sliding stability of the dam is determined considering a solid body. The factor of safety against sliding is defined as the ratio of force resisting uh, sliding of the dam to the force tending to cause sliding. So here we use forces instead of the moments. In fact, here we okay, and unfortunately, here we also use forces, but you can also combine this into moments. So what do you do? Moments. Moments. You just multiply this by the radius because the. So I give you another assignment as well. So that the factor of safety in that case was determined using forces only. Check also against moment. So with the moment, you just multiply these forces by the radius because the center is here. You just know the so times the radius, and then you see what difference you need to make. So here, all this summation has to be multiplied by the radius. The same here by the radius, and see what difference does it make. So in fact, the factor of safety can be established in two ways. One, the summation of the resisting forces over the summation of the driving forces, or the summation of driving moments, right? Because it's a circle, I mean the lever arm is just the radius, so it should be fairly straightforward. So the resisting force over the sliding force. The resisting force is taken as the shear resistance developed by the base of the dam given by W tan phi. And here we are talking about entire, there are no slides. You're just talking about an entire body of the dam with one unit weight, where W is effective weight of the entire dam per unit length, and this is the angle of internal friction. I think something is wrong. This is usually called phi, not theta. Is the angle of internal friction of the dam, of the soil of which the dam is composed. The force tending to cause sliding of the dam is the horizontal component of the earth of the pressure on the upstream. So we need to change this. That should be, this should be phi. Yeah, this should be phi. Uh, so also then don't get that also phi here. Also don't get confused by these notations. So I have to make it clear to you people. For example, when you see students might ask when we present this, or sometimes just sigma, phi, or c. So these ones you consider the pore water pressure, and these ones do not. These are called total because total pressure, stress, total stress parameters are these ones, and the other ones are effective stress. The reason for this is we said when you do the test here, this is either sigma 1 if you are not able to measure the pore water pressure, so it's total stress, but ideally should be sigma 1 minus the pore water, and this is also sigma 3 sigma 3 minus the pore water. So this would be denoted as sigma 1 prime, and this would be denoted as sigma 3 prime. So when you derive parameters from this such an experiment, then you denote them as this. That means to just say they are from effective stress parameters, but sometimes you are not able to measure the pore water pressure, so you just talk about total stress. But if from a theoretical point of view, the most accurate results are from these effective stress parameters are the most representative, although because of certain reasons that we cannot measure the pore water uh, because maybe it's expensive or because it's difficult and we don't have the equipment, then we just work with the total stress parameter. So where W is the effective and then phi is the angle of internal friction of the soil of which the dam is composed. The force tending to cause sliding of the dam is horizontal, and this is the horizontal component of the pore water pressure acting on the upstream by. So that's how to calculate the pore water. H is the maximum depth of the water, and gamma is the specific gravity of water. This factor of safety can be calculated as shown. So this would be just based on the weight and the pore water pressure, and this is very approximate and can give you some result to against which you can make some assessment. But you can see the factor of safety is quite high. The Swedish method we limit to 1.5, but here you can see the factor of safety in fact is very uh, high because we know that it's not very accurate. Number 2, stability of downstream slope. Figure 2.12 shows the downstream slope of the dam separated from the rest of the dam by a vertical where h is the maximum depth and something is not right by a vertical plane. I think this is repeated. Something is wrong here. Yeah, this is repeated. Separated by a vertical plane passing through top shoulder of the downslope. The phreatic line during the steady seepage condition lying in the downslope of the dam is also shown. The average factor of safety against shear is given by the formula. Now RD is the resisting force against sliding developed due to internal friction and cohesion of the soil. HD is horizontal force acts on the vertical plane AB in the downstream direction due to earth pressure caused by the left portion. WD is the total effective weight of the downslope portion of the dam above the base. So let's see the diagram first. So figure 2.12. So this is just to show you. So but again here is just the issue, uh, the resisting force over the driving force, and the resisting force has something to do with phi and c, as you can see, and then this has something to do with the self weight. The notations are shown uh, in the in the in the diagram as shown. So the C is the cohesion, BD is the width of the base of the downstream portion, the angle of internal friction, and then this is a unit weight of the soil. H is the vertical distance from the top. This is a unit weight, the distance from the phreatic surface of the dam. So some of the notations that have been used in this formula are described here. WS is how to determine. Now this is like how to determine the safety of a certain portion of the downstream of the dam. And then we are saying the factor of safety should at least be 2. Again, a little bit higher than what is prescribed by this more accurate Swedish slip cycle method, because the actual failure surface is curved and the real factor of safety would be much less. Factor of safety against maximum shear. The downslope should also be checked against the maximum shear, which occurs at the point the base at a horizontal distance of 0.4 BD from the shoulder. So again, the factor of safety is the strength at the point of maximum shear stress over the maximum shear stress. And then the shear strength is determined by the Mohr Coulomb shear equation, which is WSH. This is sigma. This is what we say sigma tan phi. So this is this is the representation plus C. H is the vertical distance of the dam to the point of maximum shear stress, and the maximum shear strength is twice the average shear. So again, this is how to check the factor of safety against the maximum shear stress. The factor of safety should at least be 1.5. Number 3, the stability of the upstream slope. So we've checked the overall stability of the dam, downslope stability. Now we're checking the upslope stability as shown in figure 2.13. So this is the figure. So the upstream slopes is separated from the rest of the dam by a vertical plane CD passing through. So CD. So this is what we are considering. This one we are considering the stability of this portion. Now we are considering the stability of a portion up there. So again the same deal that the resisting forces upstream divided by the driving force. Same idea. The RU are the resisting forces, HU are the forces acting on the upstream portion of the dam. W is the effective weight of the upstream portion of the dam. BU is the width of the base of the upstream portion. W is saturated unit waste, WS. So again, what you need to do. The factor of safety should at least be 2. Okay. The factor of safety against maximum shear, again, idea, point of distance of 0.4 BU, like we've done before, and the same drill. I need to go through all this again. The factor of safety is about 1.5, and some, I think, series of examples there for you of how to do that. So some examples there for you, and this is how to design. So you can see, once you check the factor of safety, it's less than what is required, and then you say it's not okay or it's unsafe. That is the, of course, in your case, if it is not safe, then you have to suggest what has to be done, because that's why you're designing. So for example, here, if you find the factor of safety is 1 is less, what are the ideas? How do you increase it to 1.5? Based on the formula, this is the, anyone with suggestions? Hello? Yes? If, for example, you found that the factor of safety is not what you need, what can you do? Hello? Yes? Someone wanted to speak. I don't know what happened. Yes? Yes? Class rep, what can you do? Hello?
According to me, you can increase the length of the embankment. You can increase the width.
Yeah, you can increase the dimension. You can see S max is the weight, right? Height. So you can increase any of this weight,
Yes.
or you can even do the, because C has something to do with the shear strength. So you even can improve the C and phi. That would mean soil improvement. You can use concrete, I mean cement, to grouting, for example. Yeah, so to make sure the strength is reaching the required values. Anyway, we proceed. So stability of the foundation against horizontal shear. If the foundation of an earth dam consists of strong stratum, such as compact gravel, coarse sand, consolidated silt, or clay, it has high shear strength and generally safe against horizontal shear. On the other hand, if the foundation consists of fine loose sand and consolidated silt or clay, it has low shear strength. Such foundation should be checked for stability against horizontal shear. An approximate method is used to check the stability. An approximate method is used. Some error here. An approximate method is used. Yes, it's used. Is used to check stability. The method is based on assumption that C5 soil should be replaced by an equivalent cohesionless soil, which would produce the same earth pressure by the C5 soil. Figure 2.14 shows the upstream portion of an earth dam on weak foundation. The soil AB passes through upstream shoulder of the dam. The thickness of the foundation stratum is H2, and the overall height of the dam measured from the rigid boundary is H1. So this is the diagram. So the stability of foundation below on the upslope, the factor of safety against average shear stress, average shear strength over the average shear stress. The average shear strength of the foundation is taken as the mean of the shear strength of the foundation at the point C below the toe of the dam and at the point B below the shoulder of the dam. So the shear strength below the toe is given by these values WFH2, and all these are this is H1, H2. All the notations are shown in the diagram. So WF is the submerged unit weight of the foundation. The shear strength below the shoulder is given as shown. So then WM is the mean submerged unit weight, and this is how to find the WM. And then WD is the submerged unit weight of the soil below the dam. Then the please note that this how to get the submerged unit weight. Submerged unit weight is because we can assume many times that students know, but they don't know. Submerged unit weight equals gamma sat minus gamma water. Okay, so hope that is clear. So this is how to find the factor of safety. So this is the S1, S2. You kind of find the average and then over the average shear strength over the average shear, and this is how to get the average shear. So the factor should at least be 1.5. A horizontal shear force S acts on the vertical plane AB, which is given as shown, where WM is the mean unit. I think this is the same idea like this is the same idea there. You can see the equations are of the same form, so and in any case these are just formulas you can with the meanings as described in the table in the diagram. So WM is the mean unit weight once more. Phi1 is the equivalent internal friction angle of a purely cohesionless soil, and this is the manipulation of the formula. So where phi and c are the angle of internal friction and cohesion of the foundation soil respectively. The factor of safety is the S max over tau max. So the maximum shear strength tau max is taken as 1.4 times the average shear stress. Some typo there. Yeah, some typo here. This should be a subscript. Anyways, there will be some typo here. Actually, I think there are some typos also previously here, because some of these things should be subscript, like H1 I saw somewhere, but it's gonna take a long time to too much effort to. I saw some typos somewhere here. Anyway, but the most important thing is you understand the meaning. So if you have a question, please feel free to interrupt and ask. So the maximum shear stress is taken as 1.4 times the average shear stress. The point of maximum shear stress occurs at the rigid boundary at the horizontal distance of 0.4 bu from the shoulder. So these are how to calculate X max, and this is the how to calculate the Wm prime, and h is the vertical distance from the upstream slope to the point D on the rigid boundary. The factor of safety should be greater than unity, okay? And then of course the examples to demonstrate what's happening here. Why is that thing? I thought it's changed. Where is it? I think it's changed. Anyway. Yeah, so some example there for you, which demonstrate how to use these those equations. So you can follow them, and then if you have a problem, you can ask. And now this is the part not very relevant for Kenya, but no, I'm not saying not very relevant. We have minor earthquakes. It doesn't mean that Kenya does. We have had a few, but can be considered minor. But also we have the Rift Valley, which can invite earthquake. Besides, you are not being trained only for being an engineer in Kenya, so still this is important for you. Now some of you might think this is difficult, but it's not at all. In fact, you already consider that you already know what you should know. It's only that the earthquake is going to induce some additional stresses or forces. So for example, you already know how to calculate the horizontal or vertical forces. Earthquake is going to make it only a little bit more, and we are going to see how to reason and drive at those values. So these are factors. You only need to add some factors on the on what you already know, so that earthquake only induce some additional forces to the system. So in the seismic regions, the stability of calculations of slope and earth dam should include earthquake forces because they reduce the margin of safety, and even failure of slope may occur in some cases. Whether the analysis is carried out by circular arc for determination of horizontal earthquake forces shall be based on the saturated unit weights of the material below the phreatic line,
and the most moist weight above it. Figure 2.15 shows the the inertial force due to earthquake as taken as alpha h. Yeah, so I already hinted this earlier about this earlier. The most important forces are the weight and the horizontal components. So you can see we have a factor alpha h. So these earthquake forces only induce uh, additional forces, but of course in the ratio of the forces that already exist. So it will have some additional forces based on the self weight of the related to the already existing forces. So nothing strange about that. So alpha h, w in the horizontal direction, and alpha h is the horizontal acceleration coefficient, and w is the weight of the slice. So that's all. The stability of the slope of the dam is checked after taking horizontal inertial force acting on the slide in horizontal direction due to horizontal acceleration while analyzing the dam by the Swedish slip circle method. So again, as a prudent engineer, this is expected of you, but I think in the assignment you don't need this because so first of all, Machakos is not in the Rift Valley, right? If it is the Rift Valley, you have to do it. Class rep, you have to tell me this. Hello? Hello? Class rep. Is the class rep still in this class? Good. Anyone else? Is Machakos? Am I in this class alone?
No, we are here, sir.
Is Machakos in the Rift Valley?
I don't. I don't think Machakos is in the Rift Valley.
Yeah, so
But we can check.
let's confirm from Google. Yeah, so that's not Rift Valley, so that's okay. You don't need to check that because maybe the issue of Rift Valley would be a catalyst of some earthquake activities, but this is not the case. So for that reason, there's no need. So this is an additional force from earthquake. This the only thing you don't know here is this factor alpha h. Now this factor could be estimated in different ways. I will show you. So then hence for the most critical combination of equal alpha hn, some typos here. Where is that? So I do not want to hear that when you are taken to work in Rwanda or I don't know where, and then you are faced with an earthquake and you say you are taught, or you work in some other jurisdiction. You need to be trained to be an international engineer. So hence for the most critical combination of a force equal to alpha hn is additional. So unless because sometimes but the issue with the earthquake is usually they come in the horizontal acceleration, but sometimes some could have different horizontal and vertical acceleration, in which case this factor will be different for the vertical and the horizontal forces. That's the only difference. But the good news is they are all related to the acceleration, which are usually pretty well measured by the geologists. They will tell you that this is earthquake of so much magnitude. The acceleration in the vertical direction is this, in the vertical acceleration in the horizontal direction is this. So all these factors are related to those magnitudes, but the good news is mostly they only come in the horizontal direction, but a very severe earthquake might come in both horizontal and vertical. But so far from the history in our region, we don't have such severe earthquakes, so that's good news for you. But you need to be aware, because you might find yourself in another jurisdiction where the things matter. And so this is the same formula here. I need you to notice how this formula changes. So it's nothing strange, because in fact it's just the things you already know. We are just building up. So just notice how different that formula is from. And is something very interesting. I might decide to ask you to show me the variation of how different is here, or this one. You can see the formula is we add the earthquake component here and subtract it on the top. I would like to discuss that here, but I'll leave that maybe in the exam. I might decide to ask what is the variation, and why do you think that is so. That is for you to think about. So here you can see the variation of the earthquake is subtracted from the top and added at the bottom. Now the factor of safety should at least be unity. And now related to the question I'm asking, you should think whether earthquake would serve to uh, cause more stability or reduce instability. That is the key of the question that I'm asking. And I think this is quite dangerous. They are saying, I think for theory this is fine, but for practice, the factor of safety should at least be more than 1, at least 1.1. Because if you say it should at least be 1, that is you're giving a slim margin of error. So should at least be 1.1 for the sake. You cannot be just exact that is 1. That means if some error occurs in your calculation, hopefully no error, but if some mishap happens in your calculation, the margin of error is quite slim, and so at least should be a little bit, the caveat should at least be slightly above 1, should that be the case. So these values usually varies between 0.05 to 2.2 depending on the location. Now here we are only talking about alpha H, but please note sometimes they can vary. This factor for the vertical and horizontal forces might vary because of the horizontal and vertical accelerations of the earthquake might be different. So this depends on the location of the dam due to various seismic zones. In Kenya, we have some map. If you Google or I think at some other courses you should have done this. There's a map that divides Kenya into several zones. Probably you should have done this in fourth year, I believe. Class rep, please guide me appropriately. Or in fifth year, there's a map where you design for horizontal forces, you design for wind, you design for earthquake, I believe. Class rep, you have done this, right?
We did the design involving wind.
Earthquake, not yet.
Yes.
Well, there's a map.
We just had some minor concepts. We just had some minor concepts, but we did not use a map.
No, you should, because so now that you're almost graduating, Yeah, you should do. You should. There's a map for Kenya, dividing the worst scenario is in the Rift Valley. Fortunately, the rest of the country is fairly fine. This is not to say that they don't experience earthquake, but because again, you do not want to make unnecessary, because these things involve money, and if in the last we use some percentile, some history, some statistical data in some years, 10,000, 300, 150, and so on and so forth. So if such an event has not occurred for the last 200 years, then probably because you design a structure to last 200 years, yourself as a designer, you will not even live to see it. So 200 years is fine. So if such a magnitude of an earthquake has not occurred for the last 200 years, then you may not need to design for it, because in 200 years, the building would have served its purpose, recuperated its amount, the project cost. So no need. So what I mean is, in this country, probably the problematic area that we consider earthquake is usually the Rift Valley. In other areas, you have to do the calculation, of course, that is due diligence. But mostly you find that because both wind and earthquake loadings are horizontal. So when you are designing, for example, you have to calculate the wind again, and then the earthquake. And now that you said you have some rough idea, the combination, the probability that an earthquake will occur and wind at the same time, is you also have to consider that probability. So you either choose the worst, but normally wind forces are higher than earthquake, because earthquake in this region is minor. But you have to check, that is the point, as a diligent engineer. In some cases, probably earthquake might be higher, but normally the practice is you choose, because the probability that maximum wind and maximum earthquake will occur at the same time is nearly zero. So you choose the maximum of earthquake or wind, of course, with the live load and dead load combination, and you design for that worst scenario. Because otherwise, you don't need to over design, and also you don't need to spend more, because you also need to do an economic design. So these values for this country are in Kenya, probably we choose the low spectrum of these values, because our earthquakes are minor. In other areas, you go towards those higher values, the areas prone to earthquakes. So depending on the location of the dam. Okay, that's the point I was trying to elucidate. In Kenya, we already have some map. It's unfortunate that you were not taught how to design earthquake, which I think should be, because you're almost graduating. If you had some years left, then probably there was hope that you would be taught. Are you doing any design courses now? Any structural design courses now?
Yes,
What is the name?
bridge design.
Yeah, actually, you should ask the teacher how to design for earthquake, because again, although in Kenya so far the bridges, the heights do not really uh, cause worry when it comes to, but just ask, so that he can try to help you understand a little bit of the what that involves. And then, so these are this explains how to resolve the forces in the tangential and radial directions. Yeah, so and then this is some procedure how to design or consider the earthquake, or in a seismic region. So damages caused by earthquakes may cause one or more of the following damages in an earth dam. may cause cracks in the core of earth dam, and leakage may occur through these cracks. So this is important, and you need to you need this to be aware, because you remember, I think a few, is it years, there was an earthquake in Tanzania, and the tremors were felt even in Nairobi. I remember. Sometime I was at home. I was still very young. I had no idea. The Some earthquake happened. I don't know, around the Kisii region. I don't know. Then I felt the kind of the wall of our house moving. Even my parents, my father is the one who told me what was happening. I had no idea. I thought the world was coming to an end. Anyway, the so you need to be aware, because even then we say these events are rare, but they happen. Yeah, and in case this happens, your design should at least still be safe, or should there's actually there are several categories of design. There is what we call uh, protection against catastrophic collapse. That means that you may not manage, in fact, to prevent failure or damage of the structure completely, because some of these things are beyond, only God can do this. So, for example, in structures, there are some categories. We give them some percentile. There's 80 percentile, 60 percentile. So because we design for the most probable, the one that can happen. But you see, you are just using statistics. There is no if, for example, you design for a magnitude of 7. Actually, 7 is very high. I'm just saying 7 is quite high. So because statistically that is what the value that has been experienced in that region. But you're not the one who decides that it will always be 7, depending on nature and God. If 8 occurs, what happens? If 8.5 occurs and you designed only for 7. So still, even though you're designing for 7, you design for what is called uh, to uh, to prevent catastrophic collapse. That means the structure may get damaged, but it cannot fall, because imagine people are inside at the time. So if this happens, because this is beyond the design capacity, and the building just crumbles, it will kill everyone inside. So we prevent catastrophic collapse. That means damage may happen, and people have the chance to be saved. Probably you have to destroy the whole structure and build it anew. That's okay, but saving lives is much more important. Yeah. If you design against 7, that means if earthquake occurs, the building is safe. It might incur some little damage which can be rectified, but the building can still be in service. Now, if anything above that occurs, of course, because you did design for that, the building can fail, but it cannot catastrophically collapse to kill people. People can be saved. Of course, the building can no longer be serviceable, but at least the objective is you save people. So this is the idea here. So even though we are saying in this country that we don't have earthquakes and so on and so forth, but we are not in charge, in fact, of when this earthquake will happen. And even when we say it's rare statistically, we have instances where earthquakes have always affected us. So still, this is the reason. So, so it may be excessive settlements. The earthquakes will also cause excessive settlements due to compression of the dam material or the foundation. It results in a decrease in the freeboard and may cause overtopping. Yes. The pore water. This is your dam, and this is probably the freeboard. Now, when an earthquake happens, these are waves, so you need to prevent this and overtopping. That's the first thing. We also need to prevent excessive settlement. And so due to shaking of the reservoir bottom, the water in the reservoir may oscillate relatively low, but waves false switches, which may cause overtopping again. And also remember this the issue of what is it called, uh, resonance. Yes, the issue, remember an uh, earthquake has an frequency, right? And then everything has their natural frequency. So if the natural frequency, unless a class rep, please tell me, at least you know this issue. You have done a vibration. There's a structural course in fourth year, should be something to do with vibration. Class rep resonance, at least you know, right? Hello? Hello?
Yes.
Resonance, you know, right?
Yeah, we did something about it.
Yes. So when if the earthquake frequency coincides with the natural frequency of the dam, then that's also an issue. That's a problem, in fact. That's a problem, in fact. So all these things have to be uh, considered, because in other words, in that case, then the vibration of the dam would be uncontrollable, and of course, uh, with the inevitable fact that the dam will be destroyed, and of course everyone downstream would be at risk. I'm going to tell you something. Just a minute. Now, in some countries, in fact, this is quite an important factor. The Because the period of an earthquake is usually uh, the frequency is calculated as 1 over t. Now most earthquakes have I think frequencies in the 0.01 second range. That's the period or the time. Now this, if you check this has coincides with the natural frequency of buildings of 10 stories, of 10 to 12 stories. So in the experience of those countries, uh, these buildings in this range, when an earthquake occurred, every time these buildings have severe damage, and people wondered why. So I also, this also need to show you that some of these things are quite applicable. It's just not an issue of quite practical. It's just a theoretical conundrum. quite practical. So they realize, in fact, that other buildings are just safe. 8 and below are just safe. 15 above are safe. But these buildings get severe. But the reason is that the earthquake, the its natural frequency of the earthquake and the natural frequency of this, especially that height, because of course you didn't say, you said you did not study earthquake, but if you did, the each building, the height has something to do with the frequency, of course, yes. So these the frequencies of 10 to 12 story are in the range of the earthquake, and then that causes resonance, and that always destroyed these kind of buildings. And so in their codes they put that some restriction. In fact, in the city code, you do not build houses in this range. You either do 8 and below or 15 and above, because of safety concerns of resonance. This was not to be done. Okay, so this just to highlight how important some of these factors are. So the natural hill slopes around the rim of this reservoir may fail and cause dumping of the rock into the reservoir, which may displace enough water to cause overtopping of the dam. Yes. Uh, so here, usually we put riprap here, right? You put riprap here, and they are massively large materials. Class rep has refused to, because you said you wanted to visit a dam. I gave some conditions that the department gave me. You should pay fees, and then we can organize. And there was silence from there. You could have seen this, I think, in Masinga. So when an earthquake happens, this material, and there is water here, this material might collapse, and then when it comes here, it will displace water. When it displaces the water, might overtop, and that's what you don't need. You don't need. So you need to make sure the stability, and of course that instability has something to do with the slope, of course, also, and the strength of the structure. So natural hill slopes around the rim of the reservoir may fall. I think that's repeated. Deposits of loose silt, if existing, the foundation may liquefy due to vibrations, may move out from underneath the dam. It may cause cracking, sliding. Yeah, these are very real issues. Piping, you should know. The Due to shaking, the pore water pressure increases. Then the soil that looked otherwise very stable starts behaving like a liquid. What does a liquid do? Just flows away. So if for some reason the foundation was resting on this kind of material, it means the entire embankment is sliding downstream, and you have no embankment at all. Because if the embankment start to slide downstream, there is water pressure. You all know everything that goes with it, and you are in problem. So these are things you need to be aware of. There may be crustal deformation associated with the movement of the fault zone. It may lift the bottom of reservoir with respect to foundation, resulting in reduction of capacity of the reservoir. This may cause overtopping. So the fault zone, we need to care about this. The Rift Valley, I've said this. In fact, there's a time the road from Narok, Maimahiu Narok, was closed somehow because the road had kind of, I think during severe rain. I'm sure maybe some of you had seen this. That road was closed, in fact, because the road had been severed by a severe fault. Of course, due to water, but the problem also is because Rift Valley is a fault zone, so an active fault zone. So these are real issues again. The dam may actually be sheared off if through a fault zone. Of course, the foundation of the dam and the two portions of the dam on either side of it may move with respect to each other, resulting in large concentrated leakage and of course consequent failure. And you guys probably have watched. I think there's a lot of movies about this. You can see, of course, those at least in movies, but even in movies they are more serious. So you can imagine in reality. And I always keep giving you the example of what happened in is it in Nakuru, some dam, Sholai, if I remember well. Yes, so these are very real issues. Of course, the one in Solai was tragic, but the mishaps of the management at the time. Of course, this is the design uh, 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 construction. So you consider the inertial forces, a graded filter, graded inter upstream core, a highly pervious material shell. The downstream shell of the earth seismic zone should be highly pervious. Now I need to see how you think. Why do you think that the material downstream should be pervious for an earthquake active zone? Anyone? And I might decide to give, if I note that you are very active in class, you might have some extra marks. Of course, everyone should be active. It's not a bribe. Uh, Anyone? Why do you think that there should be pervious material downstream, especially for an earthquake active zone? Anyone? The class is almost ending. Please, I hope everyone has recorded their attendance. So let me take this.
Yeah, I don't have any idea, but I just want to be part of the active class.
Yes, Ian. Okay, say what you think. What do you think?
I think just to prevent the earthquake, the shock waves.
How? Okay, I need you to think. Let's think. What does an earthquake do? In terms of stresses, what does earthquake do? I think I already said this. They increase what? Earthquakes increase what?
It increases the stresses.
Which kind of stresses? Class rep.
It comes along with the seismic waves that goes.
It's true. I think I said this very clearly before. Earthquake increases the excess pore water pressure, right?
Yeah, that's right.
It increases the excess pore water pressure. So, what does excess pore water pressure mean? To dissipate the excess pore water pressure, you need to increase the seepage, right? The permeability, isn't it? If you increase the pore water pressure, that means the stress inside due to the pore water pressure is very high. You need to provide a way that it flows away. The water flows. The water, that means, in literal terms, it means the water is under extremely high pressure, right? This is why it causes piping of a top, and in fact, in a massive scale, it causes what is called liquefaction, and of course, with all the problems associated with it. So so when the water is under extreme high pressure, you need to provide a way that it can flow away. So that's the reason why because otherwise, if you don't let the pore water pressure go down, then the next thing is it will destroy the embankment. So you need to provide a stopgap such that as soon as the excess pore water pressure increases, it's able to dissipate and then restore stability. Is that clear?
Yes, clear.
Yeah, so this is attendance on 31st. So this is the last part, and then so actually the explanation was here to discharge, to remove the yeah, that's the answer to discharge the excess water pressure very quickly. Then you need to consider the extra freeboard. We said previously that the freeboard should be at least 1.5 times the height of the wave, and we said a minimum value should not be less than 2 meters. There should be a thick core. Thick core, this is the impermeable layer. There should be larger section near the top, strong foundation, larger section near the top, depending on what you are using the crest for. If it's used for roadway, you also have to provide for that. So this is the end of this part. The next part we talk about gravity dam, and maybe gravity dam we need 2 or 3 more lessons. We finish, you sit your cut, and then you should be okay. No, this part does not have a cut. And the other course, so you sit your cut and then you read for your exam, and hopefully you pass and graduate. Any question? Any question?
I have a question.
Yes, please.
I have a question, but not about today. With
Yes,
regards to today's class,
yes.
what happens when a dam reaches its ultimate limit? Is it demolished or
What do you mean
after
ultimate limit
the ultimate lifetime of a dam?
of a dam? The
Like let's say the dam is designed for 500 years,
yes,
and then the sediments have accumulated and it can no longer serve its purpose.
yes. The deconstruction is there. Yes, in the lifespan, it should be deconstructed.
Okay.
Yes, you deconstruct, you remove, and if you cannot put up another dam, you deconstruction means now you remove, you destroy the what the embankment, of course with adequate safety provisions. Yeah, that's the idea, but it rarely happens, because when you design for 500, 200 years, you will not live to see it, and is all people always find that it's useful. So unless something happens, it gets silted to the level it can no longer serve its purpose. The idea should be to be deconstructed, but normally I think that rarely you'll rarely see that in your lifetime.
Okay, thank you.
Yeah. Any